Hello again, everyone, and thank you for joining us for the third and last session of this morning's webinar entitled Applications, chaired by Dr. Stefano Mariani from the Department of Civil and Environmental Engineering at the Polytechnico di Milano in Italy. Dr. Mariani is currently an associate professor at the Department of Civil and Environmental Engineering at the Polytechnic University of Milan. He was a research scholar at the Danish Technical University in '97, an adjunct professor at Penn State University in 2007, and a visiting professor at the Polytechnic Institute of New York University in 2009. He is a member of the editorial boards of Algorithms, International Journal on Advances in Systems and Measurements, Inventions, Machines, Micro and Nanosystems, Micromachines, and Sensors. His main research interests are the reliability of MEMS that are subject to shocks and drops, the structural health monitoring of composite structures through MEMS sensors, numerical simulations of ductile fracture in metals and quasi-brittle fracture in heterogeneous and functionally graded materials, extended finite element methods, the calibration of constitutive models via extended and sigma point Kalman filters, and multi-scale solution methods for dynamic delamination in layered composite. As a reminder to those of you who joined us later on in this session, this is being recorded. The recording will be made available as soon as possible on the conference webpage. If you have any questions, please feel free to post them in the Q&A box at the bottom of your screen or raise your hand. And if you're writing the question, please make sure to mention the speaker to whom you're asking the question. Now, Stefano, the floor is yours. Enjoy.
Okay, thanks, Charlotte. Thanks. And good morning, everyone. I just say a few words to introduce once again the conference and the session. So I said already something related to this when we had the starting session this week. But let me remember that this conference was born as an electronic one. And so it's not due to pandemics that we are moving to an online version, but it was born exactly this way. And I have to thank NDPI because through this platform, we're providing you the possibility of attending the conferences for free. And this is the reason why we are continuously increasing in terms of the number of contributions. So this year we exceeded 100 contributions. Actually, we are close to 150. So I have to thank also all the contributors because of this success. This year we started having these live sessions in order to have possibility to have an online discussion concerning the best contribution. So today, right now, we are about to hear 2 contributions selected out of our application session. So we start right now with the paper by Stefano Lumetti. Let me say a few words to introduce the speaker. So since last year, is scientist at the Silicon Austria Labs, which was formerly known as Carinthian Tech Center. He got a PhD in physics and nanosciences and a master in physics, both from the University of Modena and Reggio Emilia. So Stefano, thanks for your participation in this conference, and thanks for being here today. And the floor is yours now.
Okay,
please.
So thank you, Stefano, for the introduction. I will share my screen. So can you see the presentation?
Yes, yes.
Even if I go to full screen, right?
Yes, that's perfect. Yes, thanks.
Okay, so thanks for the introduction, and thanks also for granting me the opportunity to give this presentation. I will present today our results concerning the development of an analytical scheme for the calibration of magnetic position systems. This is the result of a joint work between Silicon Austria Labs and Infineon Technologies. I will start with a general introduction concerning the magnetic position and orientation systems. Then I will introduce our system of interest, what we call the mini drive, and I will discuss both its underlying operational concept and the fabrication of the real devices. Then I will touch on the readout and field computation means that are required in order to implement the scheme that we propose for the calibration of the devices. So when it comes to magnetic position and orientation systems, this is a large class of sensor systems that are usually made of permanent magnets that can move relative to magnetic field sensors. As you can see here, the motion of the magnet relative to the sensor is responsible for a modulation of the magnetic field at the magnetic sensor position. And this ultimately allows to infer information about the magnet motion by simply looking at the output of the magnetic field sensor. So several different implementations of this general principle are possible for the detection of simple motions, like can be a linear motion or a rotational motion, but also for the detection of more complex patterns of movement. These magnetic position and orientation systems are widely employed in industrial applications. And in particular, nowadays, one can count more than 100 applications in the automotive sector alone for the most diverse purposes, like, for example, gear shift detection, wheel speed sensing, ABS, gas and brake pedals, and so on and so forth. Magnetic field sensing principles are actually remarkably competitive because, first of all, the non-contact operation of the devices makes them practically wear-free, which result in long lifetimes that can extend up to decades. Then these systems are also robust against environmental contamination, which makes them suitable for applications in harsh environments, like, for example, in machinery where water, oil, or other dirty substances can be used. And finally, when combined with CMOS sensor technologies, these magnetic position and orientation systems can offer high resolution at a very high cost efficiency. Several sensing technologies are available today for the measurement of magnetic fields. When it comes to industrial applications, typically Hall sensors, as well as XMR-based sensors and flux gate sensing technologies are the mostly employed solutions. And according to the application, one can choose a sensor that can measure magnetic field in 1D, 2D, or 3D. Here at the bottom, you see a typical application of 2D magnetic field detection, in particular for the linear position detection in automotive shift forks. Here you have two magnets installed on a shift fork that can move relative to a magnetic field sensor. This linear motion generates odd and even components of the magnetic field in the magnetic field sensor, and the output is then linearized typically by taking the arctangent of the even over the odd component in order to achieve a one-to-one correspondence between the position of the magnet and the sensor output. The development and the design of magnetic position and orientation system is actually an ongoing theoretical and experimental effort that has to deal with a long list of constraints and system parameters. In particular, magnetic position and orientation systems have to be made robust against the influence of external stray fields, but they also have to cope with the fabrication tolerances, and attention must be paid, especially in industrial application, also to the cost aspect. And it's exactly in this context that we would like to place our research. What we focused on is the development of a 3-axis joystick system, the mini drive that you see here on the right. And what we wanted to show is that it's possible actually to achieve the detection of the full motion of this simple joystick system, and therefore it's possible to replace much more complex commercial systems like the BMW iDrive that you see here in the left picture by means of a much simpler design, by means of a cheaper fabrication, and but by at the same time applying a user-friendly and fast calibration scheme in order to cope with the fabrication tolerances that inevitably arise when the fabrication is done by the cheap means that I will show you later. So this is the general concept of our mini drive system. This is a 3-axis joystick where the motion detection is made by using just one sensor and one magnet. The joystick lever can rotate fully 360 degrees about its own axis and can be tilted along 4 spatial directions. So here we have the combination of a full rotational degree of freedom with 5 discrete tilt states. That is to say, the central position and the full tilt in the 4 spatial directions. The system is designed in such a way that a one-to-one correspondence is ensured between the mechanical states and the sensor output. This is achieved in particular by embedding the magnet at the bottom of the joystick lever, not in a central position, so not on axis, but with a lateral displacement with respect to the joystick axis, and at the same time by installing the magnet in such a way that its magnetization vector is perpendicular both to the joystick axis and to the lateral displacement vector of the magnet itself. Then the magnetic field is detected by a 3D Hall sensor that is placed below the magnet in central position, so in central position with respect to the lever axis. When it comes to the magnetic characteristics of such a system, you see the result here in the bottom right picture. Each full rotation of the lever, corresponds to a closed loop in the magnetic state space. So we will have finally 5 distinct closed loops corresponding to the 5 different discrete states of the system. In particular, the mini drive is designed in such a way that the separation between these magnetic cycles is made maximal, and at the same time, the intensity of the magnetic field involved in these magnetic field cycles is such that the sensor used for the measurement is able to measure these magnetic field values. Here you see a sketch of the internal structure of the mini drive. The joystick lever is shown in green, and as you see, it is endowed with a center ball that allows for the full rotation of the lever around its axis. Then a center lock mechanism is also implemented by means of this yellow head here that presses on top of the joystick lever center ball, and by means also of printed springs that are not shown actually here in this cross section, but that press upon the extremities of the yellow head and allow the joystick lever to recover the 0 tilt position as soon as the user releases it. Then when we consider the magnet, we just use a very simple off-the-shelf cubical magnet made of neodymium iron boron, and we embed it in a cavity at the bottom of the joystick lever. And finally, for magnetic field detection and sensor output analysis, we use an Infineon XMC2Go board that hosts on top of its surface a 3D Hall magnetic field sensor. This is the final result, what a real device looks like. This is made by simple 3D printing technology, so very cheap fabrication means. We chose a set of reasonable construction parameters when it comes to the distance from the center of tilt to the air gap between magnet and magnetic field sensor, for the lateral displacement of the magnet, and for the maximum tilt angle of the joystick lever. This makes the device on one hand very compact, and on the other hand stable from a magnetic point of view. But of course, the fact that we recur to 3D printing technology for the manufacture of these devices makes that tolerances in these construction parameters arise, and in particular their values are not negligible. And the fact that these tolerances are not negligible can be understood also by looking at the behavior of different mini drive devices in the magnetic field space. Here I plotted the magnetic field measurements taken from 15 different devices, and as you can see, there are huge variation for the same magnetic loops between one device and the other. This is, of course, the result of the fabrication tolerances, and this also means that we need to implement a calibration scheme in order to have a proper functioning of these devices. So before introducing the calibration itself, I will just introduce the instruments that we need to understand in order then to understand the calibration scheme. So as I told at the beginning, the magnetic position and orientation systems, the state of a magnetic position and orientation system is associated to a precise position of the magnet hosted inside the system. And what we do at the level of the magnetic field sensor is to perform a measurement of the magnetic field. And from this magnetic field measurement, we have to deduce the magnet position in order to be able to then deduce the mechanical state of the system. So we have to solve what is called the inverse problem. This is mathematically not trivial, and in particular, the challenge is to solve this problem within very fast time frames, typically milliseconds, in order to ensure a real-time measurement and real-time possibility to interact with the system. At the same time, we have to do this with limited computational resources, because usually we just have sensor ICs or microcontrollers at our disposal. What we do for our mini drive is to construct a lookup table, so a set of discrete magnetic field values associated to precise position of the magnet, and then to compare each magnetic field measurement performed by the magnetic field sensor with these values making up the lookup table. The lookup table itself is constructed by means of an analytical solution of the magnetic field equation in 3 dimensions. The calculation is done by the MagpyLib toolbox, an open source library that is based on a very user-friendly Python interface. The calculation of this analytical solution is very fast. It can be done within few milliseconds on standard CPUs. And the associated errors when it comes to cuboid magnets, like the one that we employ for our mini drive system, is very high. Comparison with the finite element simulations show that the error associated to the analytical solution is just 1%. So when it comes to the calibration itself, what we ask the user of the joystick is to provide 4 well-separated measurements for each magnetic loop. So what he does is to perform 4 consecutive rotations of the joystick knob, and in between consecutive rotation, the user is asked to register 5 magnetic field measurements, 1 for the knob in central position, and then 1 for the 4 different possible tilt directions, as you see here in the 4 plots. Then the calibration task continues by trying to fit the magnetic loops in the magnetic field space onto the calibration data that have been acquired by the user. And this is done by implementing a variation of the system tolerances. And from a technical point of view, this is done by implementing a differential evolution algorithm combined with the analytical computation of the field of cuboid magnets, as I told before. In particular, we define a cost function as the ratio of the distance from the correct magnetic loop to the distance of the nearest incorrect magnetic loop, and we try to minimize it through the application of this differential evolution optimizer. The output of the calibration procedure is a set of system tolerances that can be used then to calculate the 5 magnetic loops, and later to construct the lookup table that is then used to compare the real-time measurement of the devices and then deduce the mechanical state of the device itself while the user is using it. Here you see a summary of the calibration results. In particular, in our case, we worked with more than 10 degrees of freedom. Here we have 13 of them. 3 are associated to the position of the magnet in X, Y, and Z. 3 are associated to the orientation of its magnetization. 4 degrees of freedom are associated to the tilt angles, and finally 3 additional degrees of freedom are associated to the sensor positions. So this plot contains a lot of information, but I will try to summarize the most important ones. As you can see, the orange region just depicts the nearest bed tilt states. The nearest bed tilt, the nearest bed magnetic loop in the magnetic field space. And as you can see, when you look at the crosses that correspond to the uncalibrated system, these crosses are very close, and in many cases beyond the orange threshold, are very close to the bad tilt states, which means that if we do not calibrate our mini drive, when we used it, we would get incorrect system state output. When we take instead the calibrated state that are shown as circles that you see here at the bottom of the plot, we are instead much more precise, and we are much closer to the correct magnetic loops that identify the correct state of the system instead of the wrong magnetic loops. So the calibration is needed for a proper operation of the mini drives, and in particular, this plot also shows that using just 4 points for each magnetic field cycle is sufficient to achieve a very good result, as in particular we see that if we compare with the calibration done with much more point, 250, which is shown by the red line that is partially covered by the colored dots, well, we can see that the result is almost the same. So the 4-point calibration is very efficient, is very easy to be implemented by the user, and gives a very good result when it comes to the final calibration of the device. So to summarize the conclusion, we fabricated a mini drive system, that is to say a 3-axis joystick with just one sensor and one magnet for the detection of the motion. And the manufacturing technology chosen was very cheap and inexpensive 3D printing technologies. Of course, this gives rise to fabrication tolerances, so a calibration of the devices is needed. For this, we, on one side, solve we solve analytically the equations for the magnetic field generated by cuboid magnets in order to construct lookup tables, and then we solve a multivariate optimization problem by means of a differential evolution algorithm in order to get the relevant fabrication tolerances of the system. This can be done really very fast, and the user is just asked to implement a very user-friendly and simple calibration scheme. We have shown that more than 10 degrees of freedom can be calibrated within just very few seconds on standard CPUs of standard computers. And this general analytical method also holds potential to be extended to the design and calibration of other magnetic position and orientation systems, more complex, but still very cost efficient. Thank you for your attention.
Okay, thanks, Stefano, for the very nice and interesting presentation. Okay, so we are open for discussion now. Is there any questions in the audience?
I have one short question.
Yes,
this
please.
permanent magnet that you use, is it possible to have, you know, the magnet's parameters change over time, let's say over a year or maybe longer period of time? Is it possible to have, you know, the properties of the permanent magnets vary and the calibration is no longer effective? Is this technically possible? I am not an expert on permanent magnets, but from a material science point of view, is this something, you know, possible, and is this a major problem or not?
So the magnets that we use are made of hard ferromagnetic materials, so it is very difficult to change their magnetization properties. Mm-hmm. And in principle, so far we have experienced a very high stability when it comes to the magnetic characteristics of the magnets. What
about temperature?
The magnets that we use are made of neodymium iron boron. The Curie temperature is 350 degrees, but a deterioration of the magnetic properties can start at lower temperatures, at around typically 100 Celsius degrees. So of course, high temperature operation of the device is not advised. Okay. But when it comes to room temperature operation,
is this calibration done at the factory or when the product is delivered to the user? Who will do the calibration?
So this can be done actually when the product is delivered to the user. Okay. The user just register 4 different states for each sorry, yeah, for each rotation, I mean, it rotates in 4 different rotational positions, the knob of the joystick, and then it acquires measurements for the different tilt states. So it's very simple. This makes 4 measurements for each magnetic field loop. And then the rest is done by calculations on the microcontroller.
Okay.
By means,
Thank
yes, of very simple Python scripts.
Thank you.
Okay, thanks. So I have a question related to the loop you were mentioning. So since it will be the user to do this calibration, so is this procedure turned out to be kind of optimized one? So do you have a kind of redundancies in the data in order to assure that the calibration is robust enough? Because you can maybe imagine that the users are not really good in doing as you do instead in the lab.
Yeah, this is actually when the implementation of this differential evolution optimizer comes into hand, because it's what you say is absolutely true. The user has to move the knob by hand, so he may not be super precise in achieving the maximum tilt angle or in performing 90 degrees rotation of the knob. But nevertheless, the calibration scheme is capable of calculating the good system fabrication tolerances and then to generate the correct magnetic loops in order then to construct the lookup table necessary to detect the magnetic, I mean, the state of the system during real-time operation. So what you say, yeah, is absolutely true, but the calibration scheme is made so that it can also compensate for these uncertainties when it comes to the acquisition of the calibration data.
Okay, thanks. Any other questions?
Stefano, I have one more question.
Yes, please.
Is it possible to have, in principle, multiple permanent magnets and multiple magnetic sensors? I don't know whether it will, be extremely expensive for the applications that you are interested in. Just to add more redundancy and maybe also improve precision by additional sensors. So will it be, from an economical perspective, feasible to add, let's say, one more magnetic sensor and one more magnet, and probably change the algorithm and improve the accuracy or the robustness of the system? Is it, from an economical perspective, feasible or not?
So from a technical point of view, you can consider the possibility. Actually,
Yes.
from a general point of view, the magnetic position and orientation systems are made of multiple magnets that move relative to multiple magnetic field sensors. But in our case, yeah, I mean, the aim was maximal simplicity, but at the same time, correct device operation. Okay. So in principle, by combining this simple design structure with just one sensor and one magnet with a fast and analytically based calibration procedure, we were able to achieve the full functionality that we wanted.
Okay, thank you.
Okay, thanks. So if we don't have any further questions, so we thank once again Stefano for the very nice presentation.
Thank you.
And I think we can move to the next speaker, Onur Toker, who is Associate Professor of Electrical and Computing Engineering at Florida, Polytechnic University. Just to mention something concerning his curriculum. So he got a PhD in electrical engineering at Ohio State University and a couple of masters, even there in mathematics and electrical engineering. And then we have to return back to the bachelor to be back in Istanbul, Turkey. And so Onur, thanks for being here today with us. And even because of the hour, I think, as you are connected from Florida, right? So thanks for being here. And now the floor is yours.
Thank you very much, Stefano. Let me share the screen. The title of our talk is a synthetic wideband radar system using software-defined radios. And this is a joint work with Dr. Özdemir at North Carolina State University. And we would like to acknowledge the funding agencies, NSA Fund and NSF Grant, and also our university and the Advanced Mobility Institute provided support for this research. So this is the outline of the talk. I will start with a short summary of frequency modulated continuous wave radar. So this is basically a radar imaging system using software-defined radios, and there are so many different types of radar architectures, and among those frequency modulated continuous wave radar systems, they are quite popular because of their simplicity. And what we are proposing here is inspired by, but it has a different architecture, and it is implemented by using what's called software-defined radios. I will also explain what's a software-defined radio. And basically, the radars and their imaging accuracy are directly linked with the sweep bandwidth. This is also a technical term that I will explain when I go over the architecture of the radars. So basically, to do more accurate radar imaging, you need to do higher bandwidth sweep. So if your sweep is, let's say, 500 megahertz, you will have a reasonable accuracy. But if you go to a couple of gigahertz sweep, then you will have much higher range resolution. And that may not be very easy to achieve by using pure RF components. So this is basically what is proposed here is a synthetic wideband technique, how to do wideband sweeps by using software-defined radios over a longer period of time by slowly changing the local oscillator frequency. I will also show experimental results, and at the end, I will make a concluding remark. Okay, so let's first look at the standard frequency modulated continuous wave radar architecture. Okay, so in a FMCW radar, we have basically a voltage controlled oscillator, and we have a ramp signal generator. So this is like a triangle wave or sawtooth wave. And the frequency of the oscillator changes linearly over time from a minimum value to another maximum, and then this repeats. You may have a time gap between each cycle, but basically you have a linearly increasing frequency, and it goes to a transmit antenna, possibly with some amplification. And then you have a copy of the same signal going to a mixer, and the mixer basically mixes the copy of the oscillator signal and the signal coming from the receive antenna. And you may also have here amplifier stage, and then the mixer output is digitized, and then you do some signal processing to estimate the target, to estimate its size. You can do range and velocity estimation. So this is the general architecture, but to be able to get high bandwidth sweeps, okay, you need a better VCO. And this is typically a problem, okay? So what is proposed here is how to achieve much higher bandwidth compared to the voltage control oscillators, which are available as RF blocks. Let me show examples to be more precise. For example, this is a frequency modulated continuous wave radar system, and the voltage controlled oscillator that we have here is basically, it is this guy, and it is operating at 2.4 gigahertz, and it generates around 400 to 500 megahertz sweep. So it starts from 2 2 gigahertz and goes up to 2.4 or 2.5. Okay, and again, for higher resolution imaging, you need to cover a larger bandwidth. Okay, as you cover as you increase the bandwidth, you get better resolution. Okay, but this system does not allow us to go from, let's say, 1 to 3 gigahertz. So the VCOs operating at those frequencies, they may have sweep bandwidth equal to 10% or 20% of the operating frequency, but we would like to achieve a much higher sweep bandwidth for better high resolution imaging. That's the key problem. This one is a simple construction. It's called the MIT radar. Now, we also have a 2.4 gigahertz radar system. And just to give you an idea, this is basically the VCO that we have here is capable of going from 24 to 28. So we can cover a 4 gigahertz frequency band, and 4 gigahertz will definitely result much better imaging accuracy compared to 400 megahertz sweep or 500 megahertz sweep. Again, the system is similar to the previous architecture. There is a VCO here. There is a splitter here. This goes to the transmit antenna. And here we have a balanced IQ mixer. And here we have an amplifier amplifying the signal coming from the receive antenna. And this IQ, it can be either viewed on a scope or it can be connected to a computer-like system for processing. Okay, and here we have the received signal. So this is the ramp signal going to the voltage controlled oscillator, and this is the signal that we see at the I output. And here we have a single reflector, and the frequency of the sine wave that we see here is basically proportional with the target distance. Okay, again, just to explain the concept of the frequency modulated continuous wave radars, here there is another experiment with a 77 gigahertz radar. Here the sweep bandwidth is also around 4 gigahertz. And this is what we see if we have a vehicle which is 5 meters away from the radar sensor. So this is the radar sensor, this is a garage, and there is another vehicle parked 5 meters away from this. And this is the FFT of the signal that we get at the I output. Okay. Now, before we finish the discussion, there is also a two-dimensional technique, okay, for moving target identification. So it is in principle possible to combine multiple I-channel measurements into a matrix and use image processing techniques and obtain what's called radar heat maps or range velocity heat maps. And you can basically identify moving targets in a crowded environment, because in a radar application, you will have reflections from multiple different targets. Okay, so if the target is moving, there is a way to identify it in a crowded environment. So what we are doing here is, instead of using the previously shown solutions for radar imaging, we are proposing the use of a software-defined radio-based approach for radar imaging. So a software-defined radio is just an IQ mixer for up conversion and an IQ mixer for down conversion. But you can have, and the IQ data comes from the computer using this USB cable. You can have here 2 transmit and 2 receive antennas. You can have just 1 transmit, 1 receive antenna. You can have multiple different combinations, but it is practical, and it has software supported by both Python and MATLAB, as well as it has its own software platform called the GNU radio. So it is cheaper and it is also quite practical. But what is also important here is that this does not require any RF experience. You can simply, without having any RF experience, you can use these components. And the local oscillator here is very easy to tune by using this USB cable connection. The software running on the host PC can change the local oscillator frequency. So these software-defined radios operate from almost DC up to 6 gigahertz. So you can easily generate 4 or even 5 gigahertz sweep and achieve very high resolution imaging. Okay, again, the quality of the imaging or the accuracy of the radar imaging highly depends on your sweep bandwidth. Okay, and the key idea proposed here in this paper, it's basically synthetic wideband approach. What is synthetic wideband? Synthetic wideband approach is instead of using a VCO, we basically use a software-defined radio, but we slowly change the local oscillator frequency. And in this paper number 6 that we cite in the paper, in our paper, they use a time domain technique to combine multiple measurements. So the idea here is in the software-defined radio, you do multiple measurements by changing the local oscillator frequency, and then later you combine those to obtain high resolution radar imaging. So in the paper number 6, they also do multiple experiments, but then they combine the data in the time domain. Then we also have almost at the same time 4 and 5. This is a researcher in France, and they use the noise radar technique to combine multiple measurements to obtain high resolution imaging. So the key idea is how to do high resolution imaging by using synthetic techniques, and paper 6 is doing it by using a time domain approach. 4 and 5, it's a different technique based on the noise radar. What we are doing is basically a frequency domain approach. So we consider the physical medium between the transmit and receive antenna, and we just do basically frequency domain system identification. We just feed from the host computer a sine wave and look at the received sine wave at the baseband. And by looking at the phase shift between the transmit and the receive baseband sine waves, we estimate the attenuation of the physical medium at a particular frequency and the phase shift. And by changing the local oscillator, we basically identify the physical medium's frequency response over a wide band. That's the key idea. Okay, so but once you have the transfer function of the physical medium, then you can use it to estimate the result of frequency modulated continuous wave radar system or a noise radar system. Okay, so this is basically the summary of the approach. Now let me show you a couple of experiments that we have done. Here we have 2 antennas. These are CAN antennas, and we have a target here on the left, and the target moves about 15 to 20 centimeters. Okay, and on the left we see the radar images. Okay, this is a one-dimensional FFT based, and the large peak that we see here at 2 meters, it is because of the line of sight coupling. Okay, we have long cables from the software-defined radios to the transmit and receive antennas. And as I move the reflector, we see this peak basically moving by the same amount. Okay, now as you see, we have a complex reflection pattern. We have reflections from the wall. I cut it from here, but we have also reflections from the wall. We have small peaks, and it is difficult to interpret all of these peaks, but this one is definitely from this reflector that we have in figure 4. We have also done a different experiment. Okay, this one is a more controlled experiment. Okay, so here we have the this is the transmit signal. Transmit signal goes through a long delay line. So this line basically represents a signal delay, and then we have here a splitter. The signal is split into 2 parts. One part travels a longer distance, another part travels an almost 0 distance, and then they are combined, and then they travel another distance. So basically we are basically generating a more controlled environment with a reflector at 2x distance and another reflector at 3x distance, like 2 meters and 3 meters, or 4 meters and 6 meters. And when we look at this system and get the data, we see this FFT plot. This one is the longer path, and this one is the effect of the shorter path. And we see also an attenuation, like 20% loss, which is probably because of this cable. Okay, so and when we look at the tap indices, we also see a ratio of 2/3, which verifies, which looks consistent with the physical setup that we have here. So all of these experiments, they are done with they are done at the 2.4 gigahertz range, but they all have high bandwidth. Okay, high bandwidth sweeps for better resolution imaging. Now we have basically a GitHub repository mentioned in the paper, and we have 2 software solutions for this setup. One of them is based on a pure Python approach, and you basically run a Python script which changes the local oscillator frequency, and it performs all the measurements one after the other, and then combines all the data and generates a high resolution radar image without using any radar equipment, just using a software-defined radio. But we also have a different setup which doesn't depend on any Python application or any Python setup. This is a GNU radio graph, which is kind of standard in software-defined radio research community. So this is something that can be operated by an average graduate student with reasonable training. And when we run this graph, okay, this one basically connects to a MATLAB or Octave application and passes the received data to a MATLAB script or Octave script for processing. So basically, it's also possible to operate this synthetic wideband radar imaging system just by using the standard software tools, the GNU radio and the Octave, and it's possible to pass data from the GNU graph application to MATLAB for processing and analysis. Okay, so this is the final slide. Basically, what we proposed here is similar to the 2 recent papers for synthetic wideband imaging. The key idea is for high resolution radar imaging, you need to generate a high bandwidth sweep. And we are all of the papers that we cited, okay, both the ones in France and also the recent IEEE paper, they are all using software-defined radio hardware to achieve high resolution radar imaging. but the techniques that they use to combine the data to achieve synthetic wideband imaging, it's different. What we propose is a frequency domain approach, and all of these techniques basically are based on changing the local oscillator frequency gradually, collecting data at each frequency, and then combining them to do radar imaging. That's basically the conclusion slide.
Okay, thanks, Onur, for the interesting, very nice presentation. And as usual, now we're open for discussion. Is there any questions in the audience? So I have a couple of curiosities, if I may. So first one is, so maybe, sorry if the question is a bit sloppy, but so you showed all the results in a kind of static environment, meaning that the antennas, yes, they are fixed, and so they do not move. And what about the capability in case of a dynamic environment, where you have both so the other objects that you want to track to move, but also the antennas?
Yes, this is a very good question. Okay, the weak point of the synthetic wideband imaging is you need to take the measurements by changing the local oscillator frequency, and a single scan, okay, it can take let's say 30 to 40 seconds. And during this time period, the environment must be stationary. So you achieve high resolution radar imaging, but the environment must be static. But if you use a, let's say, much higher frequency voltage controlled oscillator, in that case, the hardware will be more expensive, but you will be able to sweep, do a single sweep in maybe a couple of milliseconds. Indeed, the all of the radar systems, which are based on voltage controlled oscillators that I showed in the PowerPoint presentation at the beginning, they can do a single sweep in 1 millisecond, okay? But the one that we propose is a simple hardware solution to achieve, let's say, 4 or 5 gigahertz sweep bandwidth. But the disadvantage of all of these synthetic wideband techniques, you need to do the measurement over a longer period. So okay, moving target identification looks probably very difficult, or maybe even not possible.
Okay, got it. So basically, you already understood. So you already answered my further curiosity, because it was related to the resolution you can have with this setup, and so basically, I got that. So it's as usual a trade-off between the costs of the instruments and the accuracy you want to achieve, obviously. Yeah. Okay. Yeah. Okay. So any other questions? I don't see any other in the audience. So I thank once again Onur for the interesting presentation. And I can conclude this session thanking again the two speakers, Onur and Stefano, for the very interesting topics they discussed. So my virtual applause goes to them. So it was really a pleasure to chair this session. And I just close remembering that we have next session this afternoon. It is at 3 p.m. Central European time again. And this is again a cluster of sessions, because we will have sessions related to smart cities, physical sensors, and wearable sensors. So next sessions will be next week, starting on Monday, so after the one that we have this afternoon. So I thank again Charlotte for introducing all the sessions. I thank you all for staying here with us today, and so stay tuned for the other sessions that we're going to have. Okay, thanks to everyone. Bye-bye.
Thank you. Bye.
Bye-bye.